Now I'll be talking about the calculus that I explored in relation to neural networks and how neural networks traverse in a feed-forward manner in order to compute gradients with partial derivatives, and then how they're applied to do backpropagation on that same architecture. And this is done in order to optimize for lowering the loss or cost or increasing the accuracy, whatever metric you're using it for. So in order to understand how you would do forward and backpropagation with linear regression, with linear classification, MLPs that is generalizable to pretty much every single architecture that uses this sort of framework with backpropagation and forward propagation, you would want to understand the basis of derivatives. And to help understand derivatives, the way I'm going to be describing it is using this graph where we're trying to understand how 1 unit of time changes the amount of distance you travel. So again, given a unit of time, how much distance would be traveled? And what we want to do again is find the best ratio. So in order to do this, let's say we had a graph over here that I'm drawing, and this was the line, and this again was time and distance, whatever traveled. How would we find the slope of this? Because we want to find the rate of change, right? We want to find this ratio. How do we find the rate of change? We would usually, what we want to do, and let's call this function s of t, doesn't really matter, is you would want to find the rise over the run of this line. And that's how you find the slope. That's how you find the rate of change. So what if we had something more complex? Something like this function s of t over here, which looks like this. How would we find the rise over the run for this? And something to keep in mind is the slope of this weird function s of t, it changes at certain points. So this slope is different from this slope, is different from this slope. And so in order to find this, what we will do first is we'll take some sort of arbitrary 2 points. Let's say we want to find the slope over here. What we want to do is we want to find 2 arbitrary points, this one being the first one where we want to find the slope of, and then we'll take this. But because it's arbitrary, you don't exactly know what the t-value increment is. And what I mean by that is here we will call this t, represent the value of time. And here we will call this t plus d of t. So d of t is something that we don't know what the value is, right? It's just like an increment of change. So this run, the difference between this and this is dt. Okay, and then let's say we wanted to find the equivalent of this, but on the y-axis. What we would do then is, let me zoom out a bit. We would go this way, and then this would be s of t. And then for this one, this would be s of t plus dt. Okay, so now that we have done that, let's say this is the rise. Now we want to compute the rise over the run. So how are we going to do that? We have this equation here which shows that ds over dt, we need to find that. And what this means is, again, like the relation of time to distance traveled with relation to t, this is just the best ratio. And in order to do this, we wanted to find rise first. So in order to find rise, what we need to do is subtract this value, let me highlight it, this value over here from this value, subtract. And to find the run, we would subtract this value and this value. Now to do that, we can easily just write it here, s with the bracket t plus dt minus st over dt, because subtracting this and this gives you dt, and subtracting this and this gives you this. And of course you have to solve for it. So that is how it works. And again, because we want to find the value at this point, we can say that as this point over here, this dt approaches 0, we will find the derivative. Because at that point, let's say we have this graph, and I'm going to try to draw the same function like this, st. Let's say this was the point we're finding. At that point, when these two dots are so close to each other, the dots that we use to calculate the rise over the run, when they're so close to each other, they approach 0. They're not 0 entirely, but as they approach 0, the line that you're drawing becomes closer and closer to the tangent of the function, which would be the slope, which would be this rate of change. And that's how you would find the derivative. So to show you an example of this, let's say we have this graph, which shows the function x cubed. Now, I know this doesn't look like x cubed, it kind of does if this went like this, but this is just like one quadrant of the Cartesian plane. So let's say that this was the function, and this point was x plus h, and this point you were adding like a random h variable to x, and then this point would be f of x, and this point would be f of x plus h, which is why you get this. So let me go back. Okay, what you want to do now is, let's say you're saying that x is equal to 2 in this instance. So you have 2 plus h cubed, because you're just substituting into this. And then you're doing minus 2 to the power of cubed because you're calculating f of x that we had over here. And then that would be over h because x plus h minus x just leaves you with h. And so you want to find the value of h, right? Because that's what it's relative to. So once you calculate 2 plus h cubed minus 8, this becomes, you would realize that you get something like this. After getting something like this, you have a lot of variables, as in there's a frequent amount of dt variables showing up. Now, because we said that dt would be approaching 0 over here, and dt just represents h, by the way. So as h approaches 0, so this goes closer to this point here, and approach as in it's not 0, but it approaches 0, we can ignore this part because it would be small, very, very small. So to have a pretty good estimate of what the slope or what the derivative would be over here, you would then just calculate this, and this would be 12. This is the best constant approximation or the best ratio. And now you can think of the slope of this line over here being 12 that is tangent to this function at that point. So this becomes the derivative now, because what you can think of this is this 2 actually means x. So the derivative becomes 3x squared of this initial function here. And when we do derivatives, we also tend to put this apostrophe before the x. Now, after that, I kind of want to talk about this rule you can use in order to calculate derivatives, because obviously you don't want to do that entire step that we just did graphically. So what you're usually going to do is, let's say you had 6x squared. How are we going to find the derivative of that? I'm going to move this here. So to find the derivative of this, what you would need to do is you would multiply the exponent with this coefficient, and this would become 12x, and then you would take this and just subtract by 1. So this becomes 1. So this just becomes 12x. So let's say we had a constant now. So let's say we wanted to find the derivative of a constant 2. The constant just becomes 0. If you had, let's say x, f of x is equal to x, what does this become? When you find the derivative, this just becomes 1. That's with any constant. That's with any variable that is alone and doesn't have a power of greater than 1. And then the derivative of line ax plus b will just be the slope. It will be a. And then for some sort of reciprocal function, I also calculated that this is the derivative of quadratic function specifically. And it's like the same. It's computed the same way. If you had x squared, what would we do? Pretend this is a 1, which is the coefficient. You would do 2 times 1, which is 2. And then you would subtract 1 from 2, which makes x to the power of 1. So that becomes 2x. Anyways, more on different things or different rules that derivatives have. There's multiplication of scalars. So if there is a scalar that multiplies with the function, the derivative of it also multiplies by that scalar. So let's say you had the function x squared, and the derivative, it becomes 2x squared. Then if you had something that oh, sorry, my bad. I confused myself for a second. So if you had this be one function and this be one function, and then you multiplied by 2, the derivative of this is 2x and the derivative of this is 4x. So this is also, you can multiply by 2. So you can see that the scalars work both in the function and the derivative. The sum rule is quite similar as well. In order to understand this is function 1 and this is function 2. To find the derivative, you would get this 2x and 6x. And then from there, if you add this is 8x, which counts as the derivative being added up. And then if you add these two up, you get 4x2. And when you want to find the derivative, you also get 8x. So if functions can be added, then the derivatives can also be added. Derivatives. And then product rule is quite similar as well, where if you have some sort of function here, I don't know, wait a second, what did I do here? 2x times 2, 4x. Oh, okay, then it's not, this is not too relevant. Anyways, it's just like, it's quite similar to the sum rule. So if functions can be multiplied, then the derivatives can also be multiplied. Now we get onto the part of partial derivatives and then how you can take that, put that into gradient, and then do chain rule, back propagation. So this is kind of where it gets complex. Let's say you had a function of 2 variables, and I'm just going to do 2 variables to make it harder as of now, and then I'll also do 1 variable. But this is just in terms of calculating partial derivatives and then putting it into a gradient. So you have 2 variables, and what you want to do is find the partial derivative of this equation, this function, in relative to each variable. So if you're looking at x, then what you want to do is find the partial derivative of x in relation to, of f in relation to x, and then f in relation to y. So how you would do that is, let's say you're looking at the equation here. I'm going to take this annotation out for a second. There we go. Okay, so let's say we're looking at x individually. We think of y squared as a constant that we're just going to be multiplying. This is the constant coefficient. We're going to be multiplying it. And this is because we're not considering the y. So in respect to x, you would find the derivative of this, and you would get 2x, and then you would just multiply it by y squared because it's a constant coefficient. And so this becomes 2xy squared over here. Now, if we were to do this one over here, what would we do then? We would say this is the constant coefficient, and to find the derivative of this, you would get 2y, and you would just multiply that with this, and as a result, you would get 2yx squared, or you can just reorder that and get this. So that's how it works. But because we have two of these, since there were two variables, what we want to do is we want to place this into a gradient. A gradient is just a way of putting together partial derivatives of a function into a vector like this. So this is what the vector would look like. This is what the gradient would look like. And why is this important? Because once we have something like this, and we have the partial derivative of f in respect to y and x, what we want to do is, if it is something that is 2D when it has two variables, so it looks something like this, the partial derivative won't just be one line. It would be two lines. So it would be this, and it would be this, and it would form some sort of plane. And you can't just draw a one-line thing or a one-line thing like this because it is a 2D shape. So a one line is like not sufficient information to show that. And because you have the gradient, you can easily make those two lines and you get that sort of result. So let's say you had some sort of function with three variables, for instance, your vector would have a dimension of 3, so that in that three-dimensional shape, you are able to express the gradient with the same amount of dimensionality. So now that we're done that, how do the gradients actually do something? The gradients do something with a phenomenon called chain rule. And chain rule is really beneficial. It's kind of like the product rule, the sum rule, the power rule that we talked about before, but this is much more useful as it pertains to neural networks. So with the chain rule, you try to understand how the gradient from the beginning affects the end, because a lot of times in neural networks specifically, you have nested functions, and this is an example of them where if you want to find the value of y, you would first need to get x, it would need to go through the function of g, and then from there, that would go into the function of f, and then after going through the function of f, then you would get y. So it's like very nested. But what if we wanted to find how the change in x would directly impact the change in y? So in order to do that, we would need to find the derivatives and the partial derivatives, and how you would do that is you would get, so dy over dx. So this is basically saying how will the change in x go to the change in y. What you would do there is you would just go step by step. So you would say, what is the relation of x to g of x? And then what is the relation of g of x to f of x? And then from there, you would get the relation of f of x and compare that to the relation of y. And you would just be multiplying all of those together. So let's say g of x is u and y is equal to f of u. This is g of x. Just to make it simpler in terms of one variable, d of y over d of x would basically be equal to this y function first. So we're going to start from the outer to inner. We start here, and then you're saying, how does y relate to f of u of this entire thing? How do these two relate? So you would do d of y over d of u. And then after that, once you have u, you would want to compare u x and g of x, which is u. So then you would do d of x and d of u over here, and you would just multiply these together. Now, what you can also see is because it's multiplication, you could easily cancel these out, and you could get d of x over d of y. But what you're doing is you're just breaking it down into steps, so it's easier. And what you would do is, let's say you had something this, like it was really complex. You would just go this way, and you would traverse forward to, after traversing forward to evaluate a function, you could compute the gradients and go backwards in order to update the parameters. And I'll be showing that with both one variable and two variable functions as well. This is an example of it where, let's say we had the variable z, and it was affected by these two variables. what would you do? You would find how this relates to this, and 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 these two paths that you have, you would just add them. So here we find the partial derivative of d of z in relation to d of x, and then you would know that y is a constant here, so you would find that, you would find this, you would find this, you would find this, all of the things that are necessary, and then you would put them together in this equation and you would solve for it. So now that we have the gradients, we can try to understand how can we lower the cost that we have? How can we lower the loss function that we have? And I'll talk more about loss function either, but the point is when you have some sort of function, what you're trying to do is you're trying to get to the minimum point. So how would you get to the minimum point? The minimum point in any sort of function. So let's say this is the function, whoop, or actually no, let me make it a bit more clear to see where it is. This is the function. The minimum point is here, but there's also, this is called the global minimum, by the way, because it's like the minimum, but you could also consider these minimum and these minimum, and these are called local minimum. But you can notice that for every single minimum value you have, this part has a slope of 0. So over here, we have this diagram that shows that if you have one variable, then to find the derivative, you would need the tangent being equal to 0. So you could easily find that. So when you have the derivative equals to 0, you know that the derivative of this is equal to 2x equals 0. So you know that the minimum is when slope is equal to 0, when x is equal to 0. Sorry, not when x is equal to 0. Yes, actually no, when x is equal to 0, because in this point, when x is equal to 0, then y is equal to 0 as well, which is the point over here. So that's the point here. And then when you have two variables again, you need two lines. So you would need to find the partial derivative in respect to x and in respect to y, and you would need to make both of them equal to 0, so that when you compute 2x equals 0, you get x is equal to 0, and 2y is equal to 0, y is equal to 0, and this point over here will be x is equal to 0, y is equal to 0, but obviously not all the time will the minimum be on the origin. This is just for the sake of simplicity. This is the example. But over here, this is a more complex version, but it's pretty much the same thing, right? Like instead of it being not as complex like this one over here, now it's pretty complex like this because there's just like a lot more going on. So it's the same concept though. You would need to find the function in partial derivative in respect to x and in respect to y. And in order to do that, you treat, for example, in this one, y is a constant. So you would find that and you get this equation right here. And of course, it's equal to 0 because you want the minimum. And then over here, you get the same and you say, okay, equal to 0. So then you find all the values of x that could happen to x equal to 0, 4, and 6. And it's the same here. And you also find the value of y at the same time, because it's also, even though it's a constant, you can still use it to find the values. So then you have these pairs that you can form. So the different options you have for x is equal to 0, 4, and 6, and y can also be 0, 4, and 6. So then you just find as many combinations of them as you can, and as a result you end up getting 1, 2, 3, 4, 5, 6, 7, 8, right? You get 8 because you have 3 different options for both those variables. So to the power of 3, 8, and then you can evaluate each of them to see which one would be the maximum and the minimum. The ones that are x is equal to 0 or y is equal to 0, those ones you can easily take out because those ones would just be maximum, as you can see over here. And then the x is equal to 0, y is equal to 6. There's no value that goes to 6 on this graph. Otherwise, it would be outside. So you can cancel that out too. But the minimum over here, which is 4, 4, which should be around here, this would be counted as the minimum. And so that's how you find the minimum. So now that you find the minimum, what you want to do is look at the gradient descent. Is like, how can you even get to that minimum in the first place? To get to that minimum point, and this is what I explained before, I'll tell you the drawback after, but what you're trying to do is you're trying to get to the global minimum. And how you do that is you find the gradient over here. You find the gradient, and then you multiply that by this a variable, which is representing the learning rate. And the learning rate is telling you how much you need to go down. So if, let's say your point is over here and the minimum is over here, if you're learning, oh, sorry, let me throw it again with this. If your learning rate is, and you want to go here, your learning rate is, let's say, 0.1, Now the scale's like pretty, there's like a scale to it, but let's just say that 0.1 is pretty high, which it quite is in terms of machine learning. Then maybe what would happen is it would jump here, then it would jump here, and it would end up going, it could possibly end up going here, but it might just bounce back and forth. Whereas if you have a very small learning rate, then what would happen is it would just go, it would make tiny, tiny steps instead of large steps. So learning rate is just like how the size of the steps you take in order to get to the minimum point. But you have to be very careful about which learning rate you pick, because if it's too small, then there would just be so much compute used and the learning would be happening very slow. Whereas if you pick a big point, maybe it just won't even get to the maximum because it's just bouncing back and forth. It's taking too many big steps that when it reaches the bottom over here, like it can't take that many small steps to get to the minimum. So in order to do the gradient descent, what you would end up doing is you would take the new point, and to get the new point, you would take the old point and you would subtract it with the slope that's multiplied by the learning rate. But in order to do gradient descent, where do we even need to go? That's the question, right? And in order to find this, you need to look at this right here, and I'm going to explain what this means. Is if you're at this point or you're at this point and you want to go to this maximum value, how would you do so? The gradient usually tells you how to get to, how do you increase away from the minimum most of the time. What this means is, let's say you had the slope being positive, right? It's a positive slope of this point. This is the derivative of the tangent. In order to decrease the slope to step in a leftward manner, what you would need to do is you would need to decrease the slope. So that's that. And then over this point, you would need to increase the slope so that you can go, you would need to increase the slope. Yes, you would need to increase the slope, because if the slope here is -2, then it needs to be 0. So you need to increase it. And yeah, if this was, let's say 2, then you would need to decrease it. So the gradient tells you how to ascend, but you want to do descent, right? So you need to find the negative gradient, because the gradient here, what it would end up telling you is it would tell you that it would tell you a negative value. So when you update it, you would just end up going, in this case, you would just end up going up. And in this case, it would tell you a positive value. So it would just it would keep you from going, it would keep making you go up as well because it's positive, right? So we want to step left, but because the slope is positive, we just need to make it negative. And because the slope is negative, we just need to make it positive. So that means that this part over here, this would have a negative sign, so that this ascent actually becomes descent. Hopefully I explained that right. Essentially, just to summarize again, gradient tells you how to go up. So even when you want to step left, if the slope is positive, it would tell you to step right in order to go up, but that's not what you want. So you would just make the slope negative, make this gradient negative. Whereas if you have the slope being negative and you want to step in the right direction, you would need to move in a positive way. But because the gradient's telling you that no, it's negative, then you just need to add a negative sign. And that's why we have this over here. Sorry for confusing myself in the middle, but yeah, hopefully that made sense. And then the drawback of gradient descent over here, and by the way, we, as I mentioned, we update the new point with the old point minus the learning rate multiplied by the slope. So the drawback of gradient descent is when you want to find the minimum, as I said, this is the minimum, 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 just because they all have a slope of 0. But this one is the global minimum. This is like the minimum that you're actually striving for. So how do you even make sure that if you start off with some sort of variable here, that it doesn't just get to this point and just stops? Because then it would not have an incentive to go back up, because it would know that there's nowhere deeper to go from here. What you would want is just to have many initial starting points. So you can have one here, have one here, have one here, have one here. So even if some of them might land over here, or some of them might land over here or over here, there will be some that go into the global minimum. And as a result, it would just take this global minimum as the minimum after gradient descent. So yeah, it just takes many iterations and many random initializations as well. So the idea for gradient descent with 2 variables is different, because as I said, here you see you have this sort of gradient that we find when we have 2 axes, and that's why we need 2 variables in the gradient to do that. But again, as I said, the direction of the greatest ascent will just be the gradient. So the direction of the greatest descent, because you want to minimize, it will be this negative gradient. So the updated position would be pretty much the same thing that we did here, over here, but it would be with 2 variables. Also, by the way, I think I accidentally said the wrong terminology. This would not be the gradient, this would be the derivative, because a gradient is just when you have two variables. So this would be the gradient, or sorry, this would be the gradient, but this itself would just be the derivative. Okay, yeah, gradient is symbolized with this, derivative is symbolized with this. Okay, so then we update it like this. After we do gradient descent, we try to understand what the new position would be, and then we would update that with the learning rate as well. And that's how you would do gradient descent. So with linear regression, we have weights and biases in the model. And with these weights and biases, the goal is to minimize the sum of the square cost. So we want to go to the minimum point, and let's say this is the initial point. We want to go, I don't know if you can see that, but you start here and then you want to go to this minimum point. So you would just keep iterating by starting with these two weights and biases as the parameters, and then you would keep updating the values, with this being the learning rate, with this being the negative gradient, and then you would keep updating this value until you get to the minimum. This is an example of how it's done in order to minimize this loss function with linear regression. But then in neural networks specifically, you can pretty much use the same logic as well, where you're optimizing the parameters B, which is the bias, the weights, and this bias as well. And you want to get the lowest loss possible. So even for this, you would need gradient descent. And in order to do that, what we need to do is understand how every single one of these variables that we want to optimize for through this over here, we need to find the gradients first of each one of them, of each W1, W2, and B. So we're going to use a chain rule for that. And we need to find how this first affects this and this and this. And how, how the loss first affects this, and then how the prediction is affected by this, so that we are able to find how each one of these parameters that we're trying to optimize can change and minimize the loss, because that's what we want to do with the gradient descent. So if we wanted to find how the bias first is changing the loss function, so we can say that for every shift in B, how does the loss change in order to find the minimum loss with relation to B, we would use the derivative of L in respect to y hat for all of them, and then we would just change the variable here because all of these contribute to y hat anyways. So to find this this derivative here of how loss changes in respect to y hat, we would need to use this equation for loss here, and this is the mean squared error. And in order to do that, what I did was I just expanded this over here, and I found that, sorry, this might not be that clear, but I found that the derivative actually becomes minus y plus y hat. And I took that, and over here, I made this minus bracket y minus y hat. And so when you have this, and this is this one, this is this one, and this is this one, then you look at the derivative here of how B affects y hat, and how W1 affects y hat, and W2 affects y hat, and you multiply that with this value. When you have B and you're looking at this equation over here, these all just cancel out because they're constants, and they're not a coefficient to B. So all you would have is B, and to find the derivative of B would just equal to 1. So you would just do this times 1, which becomes this. So this is what you have. And then for weight 1 in relation to y hat, you only find the derivative of this, and then the rest are constants, so you can take them out. But this would basically just be equivalent to x1, since the power of W1 is 1 anyways, so it cancels itself out. And you're left with x1, and the same thing here with W2, except it's x2 this time. And so this is what you get in terms of the chain rule and how this one parameter affects L. So after you're done finding that, you can use this, and with the learning rate, you can update these parameters. And that's essentially what it says here. You find the optimal values through just iterating for W1, for W2, and for B. And then for linear classification, it's a different story, because as I mentioned, there's a sigmoid function. The sigmoid function, what it does is it acts like this, where if you have a number, but after weighing x1 and weighing x2 and adding B, the numbers are going to be all over the place in terms of classification. And with regression, it's fine because the numbers are all over the place in the data set anyways. But in classification, many times you want to determine a binary outcome, and this is what it's used for. Is like, let's say you are trying to do dogs versus cats, and your classification would be dogs is 0 and cats is 1. What we want to do is whatever number we have, like let's say we have 22 and we have 9, because 22 is so high relative to 9, we wanted to round it closer to 0. So using this, which is 0 and this is 1, we're just going to be mapping numbers. And as the number gets bigger and bigger, it approaches 1. It never reaches 1, it approaches 1. And as the number gets smaller and smaller, it approaches 0. And it never reaches 0 specifically. So that's the sigmoid function. We found the derivative over here. Where'd it go? Here. So the derivative of the sigmoid function is basically just the variable it takes in times the 1 minus the sigmoid of the variable it takes in. And we'll be applying that when we do the same sort of chain rule as well. And this time, instead of using the mean squared loss, the mean squared error, we're going to be using the log loss. And this is just like convention in linear classification. So in order to do this, we wrote down the log loss, and we want to fix the weights and the bias. So this be W1 and W2. So I again wrote down the chain rule part of this, and then I try to calculate this, and this was equal to, what was this equal to? This was equal to this value over here, which was minus, well, you can read it. But the reason why I did this is because loss symbolizes some sort of fraction sign. So if it was minus y ln logarithm y hat, then this would be taken out and you would just put y hat at the bottom as a denominator, which is what I did over here. Hopefully you can see that. And then for this part over here, I took this as a numerator and this as a denominator, and then with the addition sign, I added them both up and I got this. And then for this one over here, and this one over here, and this one over here, you just use this equation like the one here, and we kind of use a similar one over here as well. So you can see how it's quite similar in the sense that this also was multiplied by 1, so the 1 doesn't show up. This was multiplied by x1 and x2. So again, these concepts are very transferable. And then to update W1, W2, and B, you would multiply these two, and these two, and then you would end up updating it like this, and boom, you would get the gradient descent in order to get the minimum loss. And you can do the same thing with larger and larger neural networks as well by updating layers one at a time. And over here, there's so many more parameters to update because you have B1, weight here, weight here, weight here, weight here, and another B. And then that determines y hat. So let's say you wanted to find, let's find this one, which is W11 we have here. This is just to show that this is the first neuron in the first layer. What you would do first is you'd get the loss, and the loss, let's say, is here. And you would first work your way up like this. We always go from first to last. You can do the same thing. You could do last from first, but it doesn't really matter because it's multiplication anyways. So you could start off with this value of weight first and how it impacts Z1, and then how Z1 impacts the activation after sigmoid, which is A1, and then how A1 impacts Z with respect to this weight here, and then how Z impacts this y hat, which is a prediction after the sigmoid, and then how the y hat predicts or affects the loss. And then you would multiply all that together. Once you find all these based off of this, then you can update it similar to this. And this is all the sort of updates for the first layer. And then you would do the second layer. And all of this computation, it's obviously you can do it computationally on some sort of platform like PyTorch or like framework like PyTorch, but this is just doing it on hand so you can understand. So the entire purpose is going forward, you do this multiplication, you use the sigmoid in linear classification specifically. Linear regression is quite similar though. And in backpropagation, you use this sort of method of calculating the gradients in respect to certain variables and the function as a whole. And you would use chain rule to do that, to find the partial derivatives in respect to each other, and then update the weights and biases, which are the parameters that you want to update. And you would update all of them in the neural network. And you would just keep doing that on iterations and iterations until you get the minimum. So that is pretty much what I learned in terms of calculus. Thank you.